this joint work with, hold on, I have to accept this. And life is complicated. Okay, so we are back, right? Yeah.
Yes.
So this is the continuation of previous work, just with Marco Antonio Fontelos, who is at Madrid in the ICEMAT. Michael Ispizua is now a colleague at the University of the Math Department of the University of the Basque Country. And as you see, the title is The Binormal Flow and the Evolution of Viscous Vortex Filaments. The outline of the talk will be more or less as follows. First, I will show you some movies in order to try to fix the kind of guys we want to talk about and we want to describe. Then I will give you the mathematical setting. And in there will be some fundamental object, which is a singular integral, which is the so-called Biot-Savart integral. And one of the fundamental steps in our approach is the desingularization of this integral. Then I will speak about the binormal flow, which is a geometric flow of curves in 3D. And I will speak about some particular solutions, because the connection between the viscous tubes or viscous vortex filaments and the binormal flow is true through some change of coordinates that somebody has to tell you that exists, this change of coordinates. And then the traveling wave solutions is a particular and interesting case of where such a change of coordinates can be done.
Out of like a hole, which is the way actually you make smoke ring with your example.
Okay, so this is the first video where you see the evolution of a circular vortex filament. And it is clear that at least we can say that it's a curve, which should be this one, which is moving in a characteristic fashion. And the question is, what is the law for this geometric movement? Or what is the law that tells you how this guy is moving? This is the first question, but really there are more questions. For example, what is what we really see? So, of course, what you are doing here, you see, this is the typical vortex ring that you can generate by putting smoke inside of your mouth and then pushing very strongly, very abruptly. And in this case, what you have is a nozzle, right, where you have put some bubbles on the top, and then you push, you create a stream through the nozzle, and eventually this is what you see. So, of course, this brilliant curve we see here is just the width of this should be the width of a bubble, which is trapped there because it is a minimum pressure location, and that is the reason why it cannot escape. But on the other hand, you have also some other scale, which would be all these bubbles which are outside, which is another, quite likely this is what is called the viscous scale, which is where the viscosity hasn't killed all kind of the dynamics. But in any case, these are the questions. How is it moving? What is this width that we have here? And what is the outside width, the width of the outside? As you see, the bubbles which are outside are circulating, right? Are rotating around the main line. All right, so you could wonder what is this guy that appears at the beginning. He used to be at the University of Chicago. In fact, if I go back all the way up to here, this is the lab. In fact, I was in this lab, and this is the camera where they through some laser visualization they are able to detect what we have been seeing. And at that time this is back in 2013, 14. They became famous because they were able to generate, you see what he has in his hands? I will not speak about this, but they were able to generate vortices which are knotted. All right. And then, he's a collaborator with Irvine and eventually became a professor in the the University of California in one of these new campuses in Merced. All right, so the next video I want to show you is another video where the geometry is more complicated. You see, it's done in the same way. You have a nozzle where you put some bubbles, and then you create a jet, and eventually. So let's see, for example, around here, you can think that the vortex has been created. Then you could keep doing the evolution, and it seems like really you go back to the shape of the nozzle. And eventually you go back to what I saw at the beginning. So you could think that there is some kind of, say, periodic or at least quasi-periodic dynamics. And there is so there is some kind of axis switching, right? Because you start with this shape, and in the middle, you go back to a similar shape where the axis has been switching. And eventually you go back to the previous one. Again, you could ask what is this width and what is the width outside, right? And what is the law that it is detecting how this more brilliant curve you have here is moving, right? All right. So this is the second of of three movies. And this is again done by all these three movies. You can find them in a very nice video that was done by these people in Chicago, which is called Noted Vortices or something like that. You put University of Chicago Noted Vortices and you find all this. So let's do this one. This is the experimental setup that these people in Chicago had. Okay, so it is now very much the idea is that you create some shape, right? Which is very similar to the one I showed you at the beginning that the guy had in his hands, but this one is more simple. And then the filament is generated, and you see that the evolution essentially is like is rotating, but it is. Of course, this is just an impression, but it looks very much is that it is really the shape of the curve is not changing. It's just it's a rigid motion, or at least close to a rigid motion. But again, the questions are the same. What can you say about the dynamics? Which is this scale? What is the outside scale, right? All right. So I guess now I have to recover the. Yeah. So.
You can hear us?
Okay, great. Thank you. All right. So now a little bit about the math. And then, of course, we are dealing with fluid mechanics. And and there is viscosity because in principle is water. And among the structures that we are trying to describe is what we call the fluid filaments. I mean, these are structures which with vorticity, very high vorticity that concentrates around some given filaments. And the formation, the structure, and the evolution has been a central theme since the early days. And you have some few names there which are fancy. Of course, I'm very serious. Helmholtz, Kelvin, and Kirchhoff were involved in the evolution of these filaments. So if you want to describe it mathematically, the way you do it is by... Okay, so I cannot... why? So anyway, I cannot use my... I don't know why. Let me see. Okay. So I cannot use the pointer. This is the problem when I am in full screen.
But this is something related with your computer.
Yeah, so I will not able to change. So I will do. Can you? No, but this is too complicated. Okay. Oops. No, this is worse. Oops. Full screen. How is this? What happened? Here. No. What did I do? Okay, this. Okay, now. Okay, let's go back. So then mathematically, you describe the evolution by saying that the vorticity at time 0 is a delta measure, and the support of this measure is so is what you see there. Bold phase means vectors, and simple phase means the otherwise is a scalar. Right, so you have there omega of x at 0, which is the position is x, omega is the vorticity, and 0 means the time. And what I am saying is that the vorticity is a delta along a curve, which is chi, pointing in the direction of the tangent vector. So has to be a vector measure because the vorticity is a vector. So what you are saying is that the vorticity is a delta vector measure. The direction is the tangent vector of the curve, and the amplitude of the delta is a number which is gamma. So the support of the delta is the curve, the direction is the tangent vector, and the amplitude is what we call the circulation, which is gamma over 2 pi. And of course, eventually I will forget about the 2 pi. Right? So this is your initial configuration. You are given the vorticity at time 0, and then what you want to know is what happens with the vorticity at later times. All right? So then the first question is, what is the relation between the vorticity and the velocity? And of course, the relation is given by the curl. The curl of the velocity is the vorticity. And I will be dealing with the incompressible fluids. So my fluids have the property that the incompressibility, right? That the divergence of B is 0. So if you are given the vorticity, to compute the velocity is to invert the curl operator, and this is done through a singular integral, which is the one you see on the slide, right? So you see that the velocity v is obtained as a convolution of the vorticity omega with the kernel, which is the one you see there, which is x minus x prime, right? Which is a vector over the distance to the cube. And there is a wedge product in between, of course, coming from the curl. In our case, if you put in that integral expression the starting vorticity, which is a singular measure, this will be just an integral, a line integral, right? Which in fact is an oriented integral. And then this will be just an integral along the curve, and the direction will be ts ds. So, of course, what I would like to do is to find what is the velocity precisely at the curve, right? So here, if x, so if as I said before, imagine that in the integral you see on the slide t is 0, then x prime just lives on the curve. So if I take any other x which is outside of the curve, then there is no singularity. And if it is a closed curve, everything is finite, so everything makes sense. The problem is when you want to compute the velocity precisely at the curve, right? Because if you look at the kind of singularity you have the numerator is of order is x minus x prime. So the full size of the kernel is like the inverse to the distance square. So when you integrate once, it will be like the inverse of the distance, right? But this leading order will be just dictated by the first approximation of the tangent. So it will be like if your curve would be just a straight line. And in the case of the straight line, the only thing that the fluid does is just to rotate around the filament. So it is not moving. So then you have to go to the next term, which will have a singularity of the order, the inverse of the distance, and then a log appears. And if you do the math, right, then you see that the next approximation should be like at a given distance epsilon is precisely the log of epsilon in the direction of the binormal, and the size is the gamma multiplied by the curvature, plus O of 1, where the O is measured in terms of the distance, right? X, the distance of the point X to the filament. So as I said, gamma is the vorticity, kappa is the curvature, B is the binormal. And if you neglect the O of 1, what you obtain is the what it is called the localized induction approximation, which was an approximation obtained by Darrius in 1906, so a long time ago, that Levi-Civita, in fact, Darrius was a student of Levi-Civita, and Levi-Civita was very much involved also in this business until the 30s. So then the natural question is, what happens when you try to follow the filament, right? What is the evolution due to if you take Navier-Stokes equation when the initial condition is the one that I was given? So this was a quite outstanding. I mean, this was an open question for decades, and it was not answered. It was not given a first answer until 1989. And thanks to a work by Giga and Miyakawa, where they assume some kind of a smallness of the circulation in terms of the viscosity, right? So if the strength of the delta function is not too big with respect to the viscosity, then by finding the right functional space and doing a clever Picard iteration, they were able to find it, right? But what they don't do, what they don't say is what is the dynamics. So they tell you there is a solution, the solution becomes immediately regular, but what is the relation between this solution, if any, of this solution and the movies we have seen before, right? So this was the question we want to answer, and of course the first. The first answer one could imagine is to say, well, because of the viscosity, which means that the heat flow is acting with a parameter given by the viscosity, so then immediately the delta will degenerate in the normal direction to a tube where the size will be like a square root of nu t, right? So epsilon, the natural epsilon, will be the natural scale generated by the heat flow. And because you have a parameter, which is the viscosity, then the time is viscosity times the time, and this is what you see there, right? Before I had log of epsilon, and now I have changed this log of epsilon by a square root of viscosity times the time. So this would be the guess, right? And this is the result we prove. And that means that if you renormalize all these constants, because at the end of the day, log of nu t is something that depends just on t, so if you renormalize time, right, just by computing instead of using the usual time, just using the integral of the log of nu t for any given time, then the binormal flow is reduced. You can get rid of all these constants, the gamma, the 4 pi, and the log of square root of nu t, and eventually is written as you see at the bottom of the slide. The evolution of the curve will be curvature times the binormal. All right. Of course, the literature about this issue is huge, and you have a land of all this process. I mean, meaning up to what extent this localized induction approximation is true in some given examples, even in the case of a straight line, so where your filament does not move, but then you could consider more than one straight filaments, which are parallels, and so it is it's a fundamental question, and there are many people who have worked on this, and you have a long list, and by no means is complete. But in order to concrete of all this list to say what is the number, the kind of results we are interested in, I will focus your attention first of all in the one I already mentioned, which is Giga and Miyakawa, and then the one that you see in the middle, Bedrosian, Germain, Harrop-Griffiths, and the one at the bottom, Galley and Zverek. The one by Bedrosian and collaborators, it was in 2018, and it was the first result that were for more or less a general curve where they could avoid the smallness condition by Giga and Miyakawa. So Bedrosian, Germain, and Harrop-Griffiths avoid the smallness condition. But on the other hand, the time of existence is too small, and they are not able to say how what is the dynamics. I mean, they are not, at least from my point of view, they are not able to explain the videos that we saw at the beginning. The case of Gales Verac is completely different. They look just at the case of the circular ring, but they assume gamma as big as you want. So really, Galean Sverak explains mathematically what we have seen at the beginning, which is you take the vortex ring and you can imagine that the gamma, which is the strength of your delta around the circle, is any size with respect to the viscosity, and they are able to follow all the dynamics for all time, right? And in fact, if they pass to the limit in the viscosity and they renormalize the log of viscosity times the time that I mentioned before, then they obtain the binormal flow. So they have settled the question that for the circular ring, really when you go to the zero viscosity limit and you do it in the proper way, avoiding this logarithmic, then this logarithm that appears, then you obtain the binormal flow. So this is essentially the situation, right? So as a conclusion, even in the case of Giga Miyakawa, where you have a smallness condition, there was no result describing what is the evolution of a general curve. And this is the plan of this talk. So remember that the equation of Navier-Stokes is the one you see there. So you have, of course, the heat flow, which is the derivative of T with respect to omega, and the viscosity times then the Laplacian, which is the very first on the left and the very last one on the right. And then you have the convective terms, which is the tangential, I mean, it is the direction derivative of the vorticity in the direction of the velocity, which is V grad of omega, is the second term on the left. And then the first term on the right is what is called the stretching term, which is the variation of the velocity in the direction of the vorticity. And this stretching term is the one which is really a nightmare in 3D, because in 2D disappear by orthogonality. All right. Then the relation between the vorticity and the velocity is the one you see there, is given by a convolution with a kernel, which is the kernel of Biot-Savart that I appear in some previous slides. So let's first mention which is the result by Giga Miyakawa. Is they defined with a good function space, which is the so-called Morrier space that you see there as the norm of omega naught in 3/2, and they assumed it is small. Then what they prove is that essentially there is a unique solution which is regular. In fact, the velocity is c infinity, and that goes to the initial condition at time 0, and that the divergence is 0. Of course, what is the Morrier space is probably the notation is tried to describe it in the last slide, which is you have to understand omega 0 as a measure, as our initial condition. You remember it was the measure that was living in a curve. And then what the Morrier condition is to say that when I measure according to the omega 0, the measure given by the vorticity, a ball of radius r, then it is growing like the radius. So essentially it's one-dimensional, like a curve, right? If in our starting curve, I throw a ball, then the only thing that matters is the length of the curve, so which is the radius. And the gamma appears as the vorticity as the strength of the vorticity. So this was the result by Vega Miyakawa. And they do it by a fixed point iteration. Just they pass in the expression that you see in the top, they write everything like the heat flow acting on the quadratic terms, right? And they do a fixed point argument. So the solution is written as a Neumann series, really. And the leading order is the heat flow acting on the initial condition. But the initial condition is at 0. So they don't say how it is moving. This is my conclusion. So then regarding the the smallness, as I said, the first thing there was, of course, this has been studied from the beginning. So it was conjectured by Kelvin already in 1867 that if you start with a vortex ring, the velocity should be the one you see there, right? Safman find a better description, and is the one I want to insist, which you see that the velocity in the case, of course, in the case of the vortex ring, it is moving just in the perpendicular direction to the normal plane, and the sign of the circulation, which is the same as saying that the orientation of the circle determines in which direction you are moving, if up or down, right? So imagine that you are moving up, then Vt is the velocity in the vertical direction. So it is a scalar. And as you see there, the log of the square root of the viscosity times the time appears, which is what appeared before. The 1 over R0 appears, which is the curvature. And there is a correction, which is an O1 correction, which is the log of the radius, right? And then another O of 1 correction, which is independent of the radius, which is this 3 over 2 log of 2, and some other constant where the gamma of E is nothing but the Euler constant. And the theorem by Gallet and Sverak, which I pointed out before, is essentially that they tell you that the vorticity, look that the vorticity is not in bold, because the only thing that matters is a scalar one, is like like omega ln, which is nothing but the heat flow of the scalar omega 0 at 0, right? Because it's the value of the radius only, and it is moving in x minus at, and at is so the derivative of a is precisely v, and v is the formula you see before of sigma. So that is the reason why this result was so important. I mean, it's really settled the question of a well-known guy, which is the vortex ring. And amazingly, this was settled in 2024, and it was a paper of 60 pages that was finally, it was accepted finally accepted in Invenciones. So I mean, this tells you, probably tells you what is the situation of where we are in this problem, right? And then the other result is the one I was mentioning by Bedrasian, Germain, and Harrop Griffiths, which says two different type of results. They avoid the smallness, gamma, but in two situations. First, imagine that you start with the case of the straight line, right? E zeta is nothing but the vector 0, 0, 1. So your vortex is just the straight line. And you do a smooth perturbation, right? But in 3D, not in 2D, in 3D. So this is a 3D perturbation. And the second one is that you do a closed curve. Kind notice like the one I was saying at the beginning is a closed curve, which is nice, no self-intersections. Gamma is any size. And then you do a smooth perturbation. Then just to fix the ideas, what they prove is that for the second case is that the evolution is just the evolution of the heat flow of the initial configuration plus a smooth perturbation. But again, says nothing about the dynamics, right? Because it's the heat flow of omega 0, right? But of course, this was not an easy paper either. It appeared in Communication, European Applied Math, and it's a very long paper also. And the reason is that you avoid the smallness, the gamma. Okay, so now to tell you what is our result, is you have to look at the right coordinates. First of all, chi of t is the closed curve at time t, which has no self-intersections, and then that's so that you can construct a tubular neighborhood. I will make a picture. It will be here. Okay, so this is the picture. Let me first say it in words. So then somebody has to tell you that this chi of t has a uniform tubular neighborhood, meaning that given the curve, you create a tube, which is the points which are at a given distance. This distance has to be the smaller than the minimum of the inverse of the curvature times a constant. And also has to be, you have to pay into consideration the possibility of self-intersection. So you have to avoid that. So really constructing the tubular neighborhood is, can be more or less complicated depending on the geometry of the filament. But once you have the tubular neighborhood, then you define the normal and the binormal if you want. And then once you define the normal, you can also put cylindrical coordinates, right? You have your curve, you have your tangent vector, you have your normal plane. And in the normal point, you put cylindrical coordinates, radial coordinates, and then in the direction of t, you put a vertical coordinate. So this will be the typical cylindrical coordinates, where ER is the vector position, little n, bold n here is the normal to the curve, and then the relation is given by some cosine of a phase. And then, of course, as you see here, as I'm saying, is the position operator. So it is the x minus chi divided by the distance, where s is the arc length parameter, which gives the closest point to x in the curve, something that exists because you have the tubular neighborhood. And then given ER, you generate also the angular direction, which is E theta, which is nothing but T, which is the vertical vector, should be 0, 0, 1 if you want, cross product with the position operator, right? So these are in cylindrical coordinates, the orthonormal frame would be the tangent vector, ER, and E theta. So this is more or less the picture, right? So we imagine that you have the threefold curve that we saw in the second video, and you see in green what would be the tubular neighborhood, right? And what appears in orange will be what we call the viscous scale. So that would be the scale where you are going to see that something happens because the viscosity hasn't been able to kill it, right? So the green, you wouldn't see it, right? But what you expect to be at least probably is not as brilliant as as we saw in the videos is the orange scale. And in fact, my claim is that concerning about the question I did at the beginning, which are the scale in the second video and the first video that you see a very brilliant line, this is a much smaller scale than the viscous scale because it is the scale of a bubble. It's the width of a bubble, which is much smaller, and it is not rotating. It is just moving. While in the outside, the other bubbles are rotating. Okay? In any case, for the statement, the green you see there, it would be the tubular neighborhood, right? And the other scale that matters is the square root of the viscosity times the time. So this is the theorem. So you have your curve, which is nice. You are in the setting of Giga Miyakawa, so gamma over nu is small. And somebody has to tell you that if you give me the curve at time 0, that it evolves according to the binormal flow, and that attached to this binormal, to each time of the curve, that it is moving to this binormal flow, then that you have a uniform tubular neighborhood so that I can put moving cylindrical coordinates, all right? Once you do that, what is the vorticity? Okay, the vorticity has, as you see, there are 3 terms plus omega tilde. Forget about the third one, just to fix the ideas. Just look at the first one and the second one. So as you see, even the third one points in the tangent direction, right? It has to be a vector and it's pointing in the vertical direction, in the tangent direction. What it is changing is the amplitude of the vorticity. The very first one is the solution of the heat flow in 2D with initial condition given by gamma over 4 times the delta, right? Because it's the heat flow. So it's like the first term, you obtain it just by moving the filament with the binormal flow, and then saying that the vorticity diffuses like the heat flow, diffuses just in the normal plane as the heat flow does in 2D, right? So this is the first term. The second, and you see and because it is in 2D, right? Because it is the normal plane, then the power of the diffusion has to be 1 over viscosity times the time. So this is the amplitude. Gamma over 4 pi divided, times 1 over the viscosity times the time, which is 2D. D over 2 is 1. So the second term, which is the new one, is still in direction of t, but now the power, instead of being 1 over the viscosity times the time, is 1 over the square root of the viscosity times the time. So you have gained 1/2 power in the singularity of a square root of viscosity of nu times t, right? And again, essentially, it's like the Gaussian, except you have a rho e to the minus multiplying the Gaussian, but now has an angular dependence. And the angular dependence is the cosine. So this angular dependence is in the normal direction, right? And this goes linearly in gamma. The next term also goes in the tangent direction, but now is quadratic in gamma, which is what it is written in the one of the slides below. You see that but don't pay too much attention to the third term, just to say that it still goes in the direction of t, but it goes quadratically in gamma, which is much smaller because gamma is small. And finally, what can you say about the error? Well, the error omega tilde, right? Omega is written as this leading order plus omega tilde, and omega tilde is in the energy space, and decays the L2 norm squared decays like a power of t log of t, right? So, in other words, I am describing the dynamics, and what I am saying is that the dynamics is precisely this picture. You see, you have your curve that it is moving according to the binormal flow, and then at each given time, your curve becomes a tube, right? And the width of this tube is the square root of nu t. And of course, the L1 norm has to be preserved because it's the heat flow. So the amplitude of the dispersion, because it's 2D, has to be 1 over nu t, right? And then the correction is 1/2 square root of nu t smaller. All right, so this is the theorem we prove. So this is what I was saying. So this is the tube that appears. And now the correction, if you do the math, is precisely what it is written in this picture. It is moving, it is shifting a little bit from the curve in the direction of the normal direction, but so there is another, if you want, another scale to see this shifting, which is of the size of curvature times the viscosity times the time. So this is a tube inside the viscous tube, where you see that really the maximum of the vorticity is not obtained precisely at the curve, but slightly shifted in the direction of the normal. And how much is shifted is what you see there in green, is the curvature times the viscosity times the time. All right, so now this is about the vorticity. So now what is the new theorem? The new theorem is that this is now with Ispizua, is that, well, we don't want to pay attention to the third term. We just stop. We just want to stop at linear decomposition. At an expansion on the gamma at the linear level. So I just keep the first two terms, and the difference is now about the error term. The error term omega tilde now is not in the energy space, but it is in the Morley space, right? Why I'm going to do that? This is because now I can give a better estimate for the velocity if I do this. So in this case, the error term in the Morley space is going like again like a positive power of a square root of nu t. All right, so this is the new result. So in order to do that, I have to really desingularize the Biot-Savart integral because I have to be able to compute the velocity. So what is the meaning of, what do I mean by saying that I have to desingularize the Biot-Savart integral? And is that given the leading vorticity, right, I compute I have to be sure about the time. All right, so that given the leading order, which is the one you see there, the omega naught, right, which is pointing essentially in the direction of the tangent vector, and it is like the diffusion in a plane, in a normal plane. So what is the corresponding velocity? So then, in order to obtain the velocity, you have this expression there on the bottom, which is the velocity at rho, v0 of rho, where you see is kind of a primitive of the Gaussian, and as you see, this v0 of rho is the case at infinity as 1 over rho, because the Gaussian is E minus rho square is negligible at infinity, but at 0 is 0, right? Because 1 minus e to the minus rho square is rho square, that divided by rho gives you rho. So the velocity of the leading order of the vorticity at the center of the curve is 0, which is the typical see you see in the movies, that when you are in the eye of the tornado, your life is very nice because nothing happens. The problem is when you start to move to the border, where you start to see all this wind. I mean, all this rotate, or the velocity is rotating like crazy, right? All right, and here it is. So what is the velocity really obtained by the vorticity I have given you? So the leading order is the one I was saying, is v0 of rho. So of course you have integrated once, and because it's the heat flow, then the singularity is you gain a square root of nu t with respect to the vorticity, right? But the question is this capital V0 of rho, that at 0 is 0. If theta is the angular direction, so at rho equals 0, you don't see this term. What you see is the next one, which is precisely the binormal flow. And the rest is O of 1. I will not pay attention to them. All right? So it's like if I go to the center of the vortex, what I do see is the binormal flow, right? And I think this is the picture. No, this is the previous one. No, this is the picture. The previous one was the vorticity, which is on the top. And here you see now the velocity, right? The velocity, which is the picture you see there. So maybe it's probably better to do this. So what I'm saying is that this is the velocity. And then at 0 is 0. And and then at this distance is precisely of the value like the inverse of the distance. So it's when you move all the way up to the border of the viscous scale is where you start to see the angular velocity, which is growing like the inverse to the distance. But there is another scale, which is the one you see here, where really the angular velocity is 0, and the only thing you see is the binormal flow. So it is precisely in a tube which is much thinner than the viscous scale where you see the binormal effect. Well, I hope that the picture is more or less clear. All right. Otherwise, you can ask me afterwards. So let's keep move forward. So then now I want to say a little bit about the math. I don't have too much time. First of all, it's insisting in the expression of the velocity, which is the one in the angular direction plus the one in the binormal direction with a speed which is the log of the viscosity time, the square root of the nu viscosity times the time times the curvature plus O of 1, right? And then I think probably we'll keep this. Well, and then really, we have improved a lot this desingularization, and we have gone all the way. So this is really a real variable lemma, what is written here. We needed C3. For this one, we really need C+. And in fact, the condition which is governing which is telling you the way you desingularize the integral, I mean, how you measure the error term, you have a Dini type of condition on the derivative of the tangent vector. And the good thing and then, of course, there is another scale, which is you want to compare this with respect to this, so you want S not to be too big, and this will depend on the size of T prime, of course. But just to mention this, this is a relevant object, because it's telling you that the O of 1 of the velocity grows like the derivative of the tangent, say the curvature, but there is a log appearing. And this log appears because of this Dini type condition. Why I want to do this? Because I really want to rescale the problem. Really want to see how things depend in the curvature for reasons that I will say later on. And then once you have, this is for a given filament, so there is no time here, right? And it is just a filament. Okay, I'm putting here R, but it could be 0 to pi. I mean, it doesn't matter. Closed filament. So, but then I have to go from the filament to the tube, right? And in order to do that, I need another argument of real variable argument, which is how to fat the tube. And then now this is a proposition, and essentially is the one that allows you to write the theorem as I mentioned before. All right, so okay, so now what we do is to write the vorticity as our guess plus a correction, and then given the guess, I know the vorticity. So this is the guess, and I know the corresponding velocity because this is the proposition I have just written, and then I have to solve the Navier-Stokes equation. So I have I'm going to write it as the heat flow plus small terms that appears as forcing terms. And of course, there are the purely quadratic nonlinear terms, but then there will be the linear terms that you have the V tilde about the omega naught, the omega tilde about the V naught. And then you will have forcing terms with only and similar ones like this one and this one. So these four terms are the linear correction terms. And then you will have forcing terms because your omega naught is not an exact solution. Then you use Giga-Miyakawa's idea, and you just solve this. Now it is the initial condition for this omega tilde is 0. So this is just the solution of the heat equation with a forcing term, right? Okay, then you do it as Giga-Miyakawa do it, and then you solve the problem. It is not completely that simple because you have this correction, and then you have to put the correction inside, and then so that you have to work a little bit more. But to make the story short, the only delicate term is precisely when is the convection term. It is not the stretching term. It's the convection term that has a term which is given by the binormal flow, and which is precisely killed when you compute the derivative of your guess in time, right? So these two terms cancels, which and then so which would be what I'm saying is that in here you have what is it? This term has to be cancelled with the one which is given by V0 by this one with V0. What is V0 gradient? Yeah, by this one. Okay, so the leading order of this term is cancelled with this one, and then thanks to this cancellation, you are able to follow Giga-Miyakawa procedure. Okay, now just a few words about the binormal flow. The binormal flow is the one you see here, and it is the curvature times the binormal. Then if you differentiate once, you obtain what it is called the Schrödinger map, because if you differentiate the S here, it gives you 0, So the only thing, when you differentiate here with respect to S, the only thing that can happen is that the derivative falls here. So then you obtain this other case. And there are particular examples which are straight lines, circles analysis. But the interesting thing is that thanks to Hashimoto, that he figured out that by doing this transformation, he was able to compute what is the equation for the Xi, and it turns out that it is nothing but the cubic nonlinear Schrödinger equation that, of course, preserves the L2 and preserves many other norms. But so then if you know what is the curvature on the torsion of your curve, then you know what is the curve, right? But this is not enough, because I have to build to be able to construct the tubular neighborhood. And it is in here where to have particular solutions are particular, it is useful. So in fact, these solutions were obtained a long time ago by Kida in the 85 or 84, 85, which are nothing but rigid motions. So you imagine that your curve, sorry, here is instead of chi is capital X, is a traveling wave plus a rotation, a fixed rotation, and then you end up in an ODE that you are able to solve. In particular, the tangent vector will be nothing but a translation along the filament times a rotation. This is what this calligraphic R means. You are rotating, and in the normal direction. So there is vertical direction 0, 0, 1, and the normal direction, and then this rotation is precisely in that. In the normal direction, and then you have a bunch of solutions that has this property. And if these solutions if these curves are really nice, they are nice, they don't have self-intersection, so you can construct the tubular neighborhood for time 0, and then you are done with for the rest, because it is nothing but a deformation. All right, so in fact, just to finish, really, okay, so the work with Fontelos was just to say, just to go forward in the Giga Miyakawa paper, saying, in your case, I can tell you how the curve is moving for later times, right? But really, I want to go further, and I want to try to say that I do see some kind of a nonlinear phenomenon. In order to do that, I need to be able to rescale the problem. So R is in this picture will be just, this is the vertical direction. So R is how far are you from the vertical direction, right? And then I want to be able to really create things which are more singular. So I really need to know how are these things for lambda large, right? And also the angle, this is the torsion. I really would like to know what happens if I put large torsions, right? Why? Because really this A is nothing but the torsion, which is the derivative of the theta. This speed, which is different to the one of the binormal flow, which is the one of the traveling wave, is dictated by this theta. And this is where we are now. Really, what we are trying to understand, we really need to understand what happens when the torsion is bigger than the time of existence we have, which is that the viscosity time. This is where are we now. So what I would like to do. So far, I can tell you what happens. This was the video number 2, right? So at some point I told you this structure changes to something like this, right? So there is an axis switching. But we are not able to do that. We are able to move, so this would be to be able to move to half of a period, and we are able to move like 1/10 of a period, right? So really, I would like to say that I really capture this change axis switching. This is with the first question. For the Hashimoto soliton, what it is called, what happens is that instead of having a closed curve, what you have is something that goes to a straight line, and you have some kind of helical perturbation here. And this is a traveling wave. So this wave is moving. And again, the theorem with Fontelos and Spizzo only says that you are moving, instead of moving all this distance, you are moving 1/10 of the distance. I would like to be able to move all the distance, right, where really something happens. This is the two things we are thinking now, and honestly, I think we have the theorem for this, but it's very delicate and we have to fill all the details. But I am very optimistic that really we can move along the filament in a nonlinear time. And the other example we have in mind is what happens when you have, for example, two lines that meet at a corner. If you want here, you put a very huge curvature. For example, like a square, and you put here something. The size of this is very, very small. In fact, we know how to do this example, but for tiny times. And then it is not clear for these small times. I cannot say what is the evolution of these waves, of these things. In particular, some waves should appear around the boundary, which are the so-called Kelvin waves that we are not able to find yet. And that's the reason why we are really interested in this kind of thing, and good dependence in lambda. And that's the reason why I insisted in the lemma of the Biot-Savart integral and how the whole thing, the Biot-Savart integral depends on the scaling, which is a real variable question. Just maybe to finish, because I see I have this picture, this is really what we have in mind. Here, instead, this is the binormal flow. Instead of the square, we have a equilateral triangle. And this is the evolution. So you see, immediately, this becomes a regular curve, but you have all these waves. We are able to capture 1/10 of this horseshoe, but we are not able to capture yet these waves. This is what we are planning. Okay, and I think that's all. Thank you.